Hello and welcome to another episode of Invalid Entry. My name is James Taylor and today we're going to be doing another episode of
Python Library of the Day. Bop, 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 bop. Hiss.
And the library of the day today is going to be PyQuaternions, which is a library to help you manipulate numbers which are kind of like complex numbers, but they have more dimensions. They actually have 4 dimensions. There is a lot of mathematics that goes into quaternions that I'm not going to go into, but I'm going to show off some of my favourite features of Python being a dynamically typed language, and I'm going to use that phrase because it's important. There are some moves at the moment to turn it into a strictly typed language, but I think that would be a down on certain functions if you do that. And you could argue, oh, you can use a generic here rather than and define these as generics. But I think that the reality is that Python, I think, is a perfectly fine language without forcing that. I'll come into why in a moment. So basically, a number is like this: x equals 3. That's a number. It can be an integer, a floating point, doesn't matter. It's Python, so it can be, not like that. It can be any length you like that. Perfectly fine. That's a perfectly fine number. You can see I've got a Mandelbrot fractal in a moment. That's going to come in handy. But Python also has the inbuilt concept of a complex, where you can pass in 2 values and it forms one number. So this is one number which has 2 parts to it. There are 90-degree angles. So you've got the real number line, you've got an imaginary number line going off at 90 degrees to it. And very quickly that allows you to work in 2 dimensions, 2-dimensional mathematical space, which is what you want to be doing when you're doing fractals. These sort of fractals, I should say, because there are other sorts of fractals as well. But these are not the only meaning of the word fractal. So the question is, what if I want another, because if I've got 2 dimensions like this at 90 degrees, I could have a 3rd dimension at 90 degrees to those 2 dimensions. I can always have 3. And then arguably I could have a 4th as well. And this is when they discovered that you actually don't actually have a point in 3D space. If you have a point in 3D space, it also has an angle or a direction it's facing in. So you end up with this thing called quaternions. So basically what I'm going to do is I'm just going to very quickly define a function. I'm going to call it add. It's going to take 2 things. Return a plus b. It's not a very good function. There you go. Now what I can do is I can do x equals 2, y equals 4, and I can do add x and y, and you can see it adds those together and returns it. But I can also do x equals complex 2, 1, make it a complex number, y equals complex 5 and 2, and then I can do add x and y, and that adds those 2 together as well. And I can make this actually, I can actually make this function foo and make it multiply together. So I can, it's called foo now, multiply those 2 numbers together, and I can multiply those 2 numbers together. It doesn't matter about the types because it's basically calling the inbuilt methods on those. It's actually calling, it's the equivalent of doing a dot, I think it's mul or something like that, on that first function to actually multiply these 2 numbers together, whatever that subfunction is. Now what you can do is you can take this a bit further now and say that we actually have a function, and I'm going to copy this function up here, which is my Mandelbrot function. My Mandelbrot formula is the coordinate you're at multiplied by itself plus some constant. And then I want to know, when you're doing a Mandelbrot, I've done a whole video on introduction to fractals, when you're building that is how fast will it leave a circle. So I want to know the absolute value. And you can do abs on complex numbers. So I'm basically saying, has the absolute position of this coordinate, has it got more than 2 away from the centre of the circle before I hit my limit on my counter? So I can do loop 10. So I can basically say, for a particular, and if I do get out, how many iterations around this thing do I need before actually it has left the circle? So what I can do is I can take a coordinate, and I can call loop on x. I need a constant, which is going to be 1, 2. It's going to be 0, 0, so to begin with, and my limit's going to be 25. And at that point, it goes straight out because 2 is obviously more than that. But if I change these values in here, if I change it to 0.5, I get different values coming out of that loop function. That loop function allows me to then generate numbers depending on how far it takes out. If I put that in a loop, and up here I have a loop, so for my size is my size of my picture, because I'm about to draw a picture. For every pixel in the loop, how many times does it take to come out? Now basically, if it takes 25, I'm going to colour it in white, otherwise I'm going to colour it in black. And actually, if I take that out for a second, I actually do have a version of this which actually does a more gradiented colour. So you can see there's some here it takes 0 to come out. I've offset this picture, so 0, 0 isn't in the middle. I've offset it because the Mandelbrot is actually shifted to the left slightly. There's some here it takes, it's already outside before it even starts, so 0. These ones come out the first, and the 2, 3, 4, 5, and so on. And as you get closer into this chaotic edge here, then you end up with the Mandelbrot fracture. Now at some point there's a difference between will come out at like infinity minus 1 position and versus it will never come out. So this line is very hard to distinguish where that line actually is. But I'm just going to put it back into it very straight. It either escapes before the 25th point or it never escapes a boundary. So it gives me that edge there. If I change that limit of 25 up to 200, it's going to take a little bit longer to run, but I get a more accurate picture at the end of it. So, but we'll go with 25 because it will keep the maths running relatively fast. So you get the Mandelbrot coming out on the screen. When Mandelbrot, just very quickly, when he was first drawing these things and using computers to help generate them, he wasn't sure if these were islands or whether actually were connected to the body. And it does seem that all the points of the Mandelbrot set are actually connected to each other, even by sometimes infinitesimally fine wires. So it's sometimes hard to tell, but there are actually connections there. Anyway, I can now use this in a loop. Complexes are built into the language. I didn't have to import anything to use a complex number. It is actually just part of the language. However, pyquaternions or quaternions are not part of built into the language. You have to import them, and there's a fantastic library called PyQuaternions. It's not necessarily the most efficient. I think there are possibly more faster. It actually uses NumPy under the hood, so it's quite a large install as well. But the thing is, it's got a really nice interface. And the other thing about quaternions is there's lots of ways to declare them. So what we're going to do here is we're just going to use one. Now the way I'm going to use one is, in fact, if I go to the page here about actually how to create one, there are lots and lots and lots of ways of creating it, which represent, if I just want, because at the end of the day, by the way, if I have 0.50 there, that is actually a scalar. It is just a normal number. It's a number which is on that horizontal axis, therefore it is a real number, has no imaginary component. But you can still say it's a complex. So all real numbers are complex numbers, just like all complex numbers are really quaternions. They're just on that flat plane, but we can now move. You can imagine us moving up and down below the bit of paper to work out where the boundaries of this shape will be. So we're going to use this method here. So we're actually going to pass in 4 digits here, but I'm going to ignore the 4th one because I can. Okay, so what we're going to do is we're going to set that to being 0.5. We're going to set that to being what was it? It was 2, I think. To begin. Oh, it would be 1. And that's going to be 0, and that's going to be 0. So I'm going to put that back to 1 and quickly run that. And you can see there I get back the answer. So I'm going to put x as being that. I'm going to set my constant to be another quaternion because I don't really want to mix and match my types. I will just say that I'll try to keep my types consistent. You can mix and match types depending on the libraries. I think I could actually do x plus 2 and see what happens. And now what we're going to do is we're going to do loop of x, the const, and 25 as my limit, and it gives me 3. It gives me the same answer. In fact, for every number I put in here, if I put 0.1 in there, it gives me 8. If I put 0.1 in there now, it'll give me 8. It's the same, mathematically the same. These things are the same. But it means that I can now, without even changing my functions, which is the great feature of Python with its dynamically typed, I can now actually generate a 3-dimensional Mandelbrot. And it's not saying that I think I've previously 3D printed a Mandelbrot. In fact, it's right here. This is my 3D printed Mandelbrot. This is not a 3D Mandelbrot. It is a 3D representation of a 2-dimensional Mandelbrot, i.e. the escape time of those points. So my mission is actually to print a 3D Mandelbrot, and there is reasons why I want to do this. I think there is reasons why I want to do this. So what we're going to do is now construct basically a lot of this time, by the way, because I'm only interested in the graph of 0 to 2, minus 2 to 2 that is. A lot of this is actually scaling the picture down. So at this point it's like minus 2, and this point here is like 1.5. So I'm just going to grab my my entire function from over here a moment, slap it down the bottom here. Now in here I'm going to nick my constant line because I define my constant here. That's my constant, and my coordinate here, I don't want it to be a complex anymore. I want it to be a quaternion. So I'm just going to put that there as a quaternion, and I'm going to pass in 0 and 0 because I'm going to do that bottom layer to begin with. So to begin with, that will error happily because you don't need to do const equals that. Now, first of all, this is noticeably slower. So running that takes 2 or 3 seconds rather than that immediate bang, it's already done, because it is actually doing more complicated maths for the extra dimensions it's in, but you end up with the same picture. So what we can do now is we can now do k equals 0.1. So I'm going to shift the plane up. So that was the slice through the Mandelbrot set at the 2 axis that we already had. Now what happens if we look at it 1 axis slightly higher up? Instead of it being 0 here, I'm going to put k in there, and we can now run it again and see what it looks like. And it will look very, very similar. I hope it looks very similar. There we go. What begins to happen is this thing here actually looks like it's symmetrical. As you go up, it actually rotates around, but it doesn't fully. These bubbles here actually appear and disappear at different angles. So there are 2 nodes at 90 degrees, but they're not necessarily carried round like a donut. They're actually little bubbles in their own right. But we want to slice this like you might slice an X-ray or see some kind of CRT scan of your brain. So what we're going to do now is we're going to put that into a loop for k in range, let's say 10. Actually, 1, 10, 0, 10. I don't want to 0.2. So we're going to upgrade it by 2 every time. We're going to tab all this stuff in, and that means it's going to draw a whole bunch of images here. Now, what I'm actually going to do, first of all, is make a big image. By going from 0.2, I know it's going to be 10, so it's going to be 10, 255 times 10, 255 times 10 there. It's going to be a big image. I actually want it to be less. That's my big image. But actually what I'm going to do here is I'm going to change this back to being from it to range 10 at this point, because k times 0.2. So that gives me the value here. And the reason I'm going to do that is because I want to use that as an offset. I don't want that being by 10 actually. I want it to be 255 tall. Just for the moment. Just see what it does. So I shouldn't have hit enter there because that's actually running it 10 times. And so they're going to output the bottom one. What we're going to do is look up very quickly, look up the pillow copy image. Here we go. It's very easy to do. My last layer, which is fine. Here we go. Right, so that image exists. What we're going to do is we're going to do big image. Yep. Dot paste image, and the box we want to go to now. It can either be 2 values or it can be so it's going to be 255 times k to move across, comma 0, so it just goes top left, and we can run that again, and it's just going to calculate the entire image. So this is going to make quite a long 2550 pixel wide image, which should be good enough for this. Remember, each slice of this will be another 0.2 high, so it's quite a big separation really. of those images. And as I said before, this is a little bit slow to run. It is what it is. Here we go, it's run already. Big image. And you can see here that those nodes change over the distance. Now again, this ball here, at this point, it's not actually connected to the main body. I said earlier these things were connected by an infinitesimal small thing. They aren't here because they're actually connected via the layer underneath. I also said I thought those things there at the top there went a donut. But you can see here, as we go up the slices on this thing, it gets thinner and thinner and thinner until there's nothing left as we get to the 2 distance away. So that's it. That is PyQuaternions in a nutshell. And the really nice feature of Python of it being dynamically typed means I didn't have to change any of my actual mathematics code. I can just throw complex or even quaternions into this thing and it will calculate my fields for me. So I've gone from working in 1 to 2 to 4 or more dimensions in a blink of an eye. And that's PyQuaternion, the library. The library does exist in other languages. I think there's an R version that's very powerful. There's definitely a C version though. So yeah, if you're interested in doing these kind of things, what I like about Python is that if you've built this, if you've written this in I don't know, Java or something, these would have types. You'd have to rewrite the basic Mandelbrot function. So if I change my function for any reason, to for example do a Julia set, then I would have to recode all my library. So I can write lots of different fractal formulas in here, and I can come back and just run it in multiple dimensions now. But that's it. I'm going to go away and play with the points of these because I'm going to try and make 3D models. But that is it for me. If you're enjoying these videos, please hit like. And subscribe. I really realised recently there's been a lot of security focused videos, but I'm going to get back onto some fun programming and maybe some 3D printing of these objects later on. Thank you very much.